Hello everyone, this is Rita, Assistant Professor of Physics from Government College for Girls, Hudiakida, Fatehbad. In this video, I will talk about basics of interference and then Young's double slit experiment. Although you have already learnt about interference in your lower classes, but still before moving on to the topic Young's double slit experiment, I would like to introduce or I would like to remind you again the basics of interference. First of all, I would like to define interference. So, interference is a phenomena in which two waves superimpose to form a resultant wave, which may be of greater, lower or of same amplitude as that of the waves coming from the coherent sources. It may be noted here that no destruction of energy is anywhere. Energy is merely redistributed so that the light energy missing at one point is appearing at the another point. So here are the types of interference. There are two types of interference, constructive interference and destructive interference. In constructive interference, if the crest of one wave overlaps with the crest of another wave, or trough of one wave overlaps with the trough of another wave, then we get the constructive interference. In these regions, we get the maximum intensity. And in the destructive interference, if the crest of one wave overlaps with the trough of another wave, or the trough of one wave overlaps with the crest of another wave, then we get the minimum intensity, and this type of interference will be known as destructive interference, as you can see in the figure. In the first figure, the crest of first wave is falling on the crest of another, and we are getting a maxima as the resultant wave, and the amplitude is increased. But in the second case, the crest of one wave is overlapping with the trough of another wave. So we are getting the least intensity, that is, we are getting the minima. In this picture, it will be more clear to you that what is constructive and what is destructive interference. See, in the part 1, wave 1 and wave 2, they are superimposing with each other. The crest of wave 1 when overlaps with the crest of wave 2, then we get the wave 1 plus wave 2, means we are getting the maximum amplitude and so maximum intensity. So this is the constructive interference. This will be the region in which the intensity will be maximum. And in the second part, the wave 1 and wave 2, they are superimposing, and the crest of wave 1 is overlapping with the trough of wave 2, and we are getting the resultant wave whose intensity is almost 0. So this type of interference will be known as the destructive interference. While explaining the definition of interference, I have used the word coherent sources. That is, the light coming from two coherent sources will superimpose to give you the interference pattern. So what is the meaning of coherent, or what is the meaning of coherent sources? The two sources will said to be coherent if they emit the light of same frequency or same wavelength, and the waves should be in same phase, or they should have the constant phase difference. If all these conditions get satisfied with two sources, then they will be said to be the coherent sources. Now, what are the conditions for obtaining a coherent source? The coherent sources should be obtained from a single source. We cannot use two different sources. The source must emit monochromatic light, means the light should have the single wavelength. And the third one is the path difference between the light sources must be very, very small. So all these are the conditions for the sources to be coherent. Now the question arises that can I use the two different sources to produce interference? Why it is the need of using a single source to produce the two coherent sources? So the answer is no, I cannot use the two different sources to produce the interference, because the two different sources can never produce the waves of same phase, because each source of light contains infinite number of atoms, and the waves which are emitted by them will never be in phase. The atoms, after absorbing energy, go to the excited states and emit the radiations when fall back to the ground state. So all will happen at the different time and in the different phase in all the sources. So that is why the two different sources can never produce the interference and they cannot be said to be the coherent sources. So in order to get the coherent sources, we have to use the originally a single source only. Now we will talk about the terms path difference and phase difference. These are the two important terms when we discuss about the interference. But we should talk about these terms only when the waves which we are superimposing, they are of same frequency. This is an important condition here. So when we use the two waves, how we can define the path difference and phase difference? Basically these two terms are used to determine the constructive and destructive interference in waves. They will decide that we get a bright fringe or we get a dark fringe. So what is path difference? Path difference is always measured in terms of wavelength. You are already aware about the term wavelength. So in the picture also I have shown you the length of a wave by the lambda. The path difference is actual measurable difference in distance that the two waves travel from source to a common point. As in the figure you can see, I have used the two waves, one in the blue color and one in the red color. If you check out about their path difference, the path difference between them is lambda by 4. Now we will talk about the another term, phase difference. Phase difference is always measured in radians. So it is basically the difference in the phases of two sinusoidal waves which are of same frequency. As you have seen in the figure that the blue wave leads the red wave by the phase difference of 90 degree. So this slide will make you aware about the relationship between the term path difference and the phase difference. You can see in the slide that the path difference is equals to lambda by 2 pi into phase difference. So this is the relationship between the two terms. If the phase difference is 2 pi, 4 pi, etc., then the path difference will come out to be lambda, 2 lambda, 3 lambda, etc. In this case, we can say that the two waves are in phase with one another, and in this case, y1 will be equals to y2. In the second case, if phase difference is equals to pi, 3 pi, etc., then the two waves will be out of phase with one another, and we can write down y1 equals to minus y2. I have also tried to explain it by the figure number 2. In the picture you can see that the first wave which is originating from the source S1 and reaching at the point P is equal to 7 lambda, and the wave which is originating from the source S2 and reaching at the point P, it is equals to 9 lambda. So you can easily write down the path difference between the two, that is equals to 2 lambda. So the path difference between S2P and S1P will be equal to 2 lambda. So it would make you clear about the term path difference. Now look at the starting point S1 and S2. You can see the two waves are originating in the same phase. But due to the path difference of 2 lambda, there will be a phase difference of 4 pi between these two waves. Now we will discuss about the conditions for interference. Before doing that, I would like to explain this figure to you, the distribution of intensity. When the two waves will superimpose on one another, which are having the same amplitude A, then due to the constructive interference, we will get the maximum intensity, and that will be directly proportional to 4A square, as you can see, and we will get the bright fringes. All the bright fringes will have the same intensity, and due to the destructive interference, we will get the dark fringes, and all the dark fringes will have the minimum intensity, which is equals to 0, and all the dark fringes will be equally dark. So this will explain you the distribution of intensity in case of interference. You can also see here that here only the redistribution of light is taking place, right? Now we will talk about the conditions for sustained interference. What are the conditions for the interference? The very first condition is the two sources producing the interference must be coherent, as I have already told you. The second condition is the two interfering wave trains must have the same plane of polarization. And the third condition is the two sources must be very close to each other, and the pattern must be observed at the large distance to have a sufficient width of fringe. You can also check it out from the relationship of fringe width, which is equals to beta. Since beta is directly proportional to capital D and inversely proportional to small d. So you will learn about this condition here. The fourth condition is the sources must be monochromatic, means they should be of single wavelength. Otherwise क्या होगा? What will happen? The fringes of different colors will overlap with each other. The next condition is the two waves must be having same amplitude, so that we can get the better contrast between the bright and dark fringes. Because you can see initially I have told you that if we take the two waves which are interfering and have the same amplitude A, then we will get the maximum intensity as directly proportional to 4a square and minimum intensity equals to 0. If the waves wouldn't have the same amplitude, then we will not get the minima as perfectly dark. So in that case we will not get the good contrast, and that will not be the good interference. Now we will discuss the another important term related to interference, that is wave front. Well, what is wave front? Before starting, I would like to tell you the term wavelet. The wavelet is the point of disturbance due to the propagation of light. You see, when we use a source of light, the light propagates in the forward direction, or according to the source it will propagate in the different directions also. So that a point which represents the disturbance, that will be known as the wavelet. And the wave front is the locus of the points having the same phase of oscillations. And if we take a line perpendicular to this wave front, that will be called a ray. So there are different types of wave front. The very first which you can see in the picture is the spherical wave front. In order to get a spherical wave front, you have to use a point source. You can see the point source, which is denoted by a green dot at the center. It is giving out the wavelets in all the directions. So you will get the wave front in the form of a sphere. So this will be the spherical wave front. In the second case, you can have the cylindrical wave front. For getting a cylindrical wave front, you have to use a linear source. In the picture you can see in the green color, it is showing the linear source and it is producing a cylindrical wave front, which is in the form of a cylinder. And the third one is the plane wave front. Plane wave front could be produced with the help of a point source or with a linear source, but for that the sources should be at a very large distance. So they will produce the wave front, which will be known as the plane wave front. You can see in the figure we have originated the plane wave front, right? Now we will talk about Young's double slit experiment. Dr. Thomas Young was the first who explained the phenomena of interference of light with the help of the experimental setup shown to you. So in this case he have used a narrow slit and then used the two slits S1 and S2, and he got an image on the screen. Like, what was the purpose of this experiment? He want to demonstrate that the light also have the wave properties. So in order to do this experiment, what he did, he took the two fine slits S1 and S2, which are having a very small distance d between them, and he placed them at a suitable distance from the original source S. Means he have created the two coherent sources S1 and S2 with the help of a single original source. On the screen he observed the alternative bright and dark fringes. The formation of these fringes could be explained with the help of interference of light. So in this experiment, the slit S, which is the original slit, that is illuminated by the source of monochromatic light, and then the spherical wave fronts were continuously coming out of it in the form of crests and troughs. You can see in the figure. Let the crests be represented by the red arcs and the troughs be represented by the yellow arcs. When these wave fronts reach the slits S1 and S2, the two slits which are placed at a distance small d, then each of them becomes a source of secondary disturbance, and secondary wavelets will start coming out of S1 and S2 in the form of crests and troughs. You can see in the picture also. These waves are of same wavelength, same amplitude and of same time period. These waves superimpose with each other, and at the points where the crest of one falls over the crest of other, or the trough of one falls over the trough of other, the resultant amplitude is maximum and light intensity would be maximum. These points will be obtained as the bright fringes on the screen, and these regions are known as of constructive interference. At the points where the crest of one wave falls over the trough of other wave, the resultant amplitude will be minimum and light intensity will also be minimum, and in this case we will get the destructive interference and we will obtain the dark fringes on the screen. Here it should be noted that the bright and dark bands obtained alternatively and they are equally spaced. So these bands are known as the interference fringes. Young's experiment has been performed in order to prove the wave nature of the light. But what happened if the light were only particles? In that case, while doing this experiment, we would get only two maximas correspond to the slits on the screen. But in actual case, we have obtained the pattern of alternate dark and bright fringes. It means, it proves that the light doesn't possess the only particle nature, and it should have some other nature also. And what is that nature? If the light had wave properties also, then in that case the light would pass through the slits S1 and S2 and it will form the alternate bright and dark fringes on the screen due to constructive and destructive interference. And in actual practice, when Young did this experiment, he observed the alternate dark and bright bands on the screen. So this confirms that the light have wave properties. So in this way, he proved about the wave nature of the light. Now I will explain you that how we can obtain a mathematical relationship in which we will get the equation which will show you that for what angles we will obtain the maximas and for what angles we will obtain the minimas. So for that we have to draw again the picture of Young's double slit experiment. As in this picture you can see that using a monochromatic source of light we have obtained the two coherent sources at the position 1 and 2, which are separated by a small distance small d, and at the distance capital D from the coherent sources we have obtained the interference pattern. Now in order to obtain the value of y, means in order to know that at what positions we will get the maximas or the minimas, we have to obtain a relationship for the path difference. You can see that from the slit 1 the waves are reaching at the point 3, and from the source 2 the waves are reaching at the common point 3, and they are interfering, and we will get some pattern at point 3. That could be maxima and that could be minima. That will be totally decided by the path difference between the waves 1 to 3 and 2 to 3. You can see clearly in the picture that the wave from 2 to 3 is divided into two parts, from 2 to 4 and from 4 to 3. Clearly you can see the path covered by the ray number 1 from 1 to 3 is exactly equal to the path covered by the ray number 2 from 4 to 3. But if we consider the ray 2 from 2 to 3, then this point 2 to 4 is having the extra path. So we will obtain this path difference from 2 to 4. In order to obtain this path difference, we will consider this small triangle 1, 2, 4 and we will find out the value from 2 to 4. That will be find out to be d sin theta. So we can say that d sin theta is the path difference between the waves coming from the source 1 and from the source 2 and reaching at the common point 3. Now we already know about the conditions of the interference, that if the path difference between the waves is an integral multiple of wavelength, we will get a maxima. So in order to get a maxima at the point 3, this path difference, that is d sin theta, should be equal to m lambda. M is some integer here which could be 0, plus minus 1, plus minus 2, etc. And if this path difference is equal to half integral multiple of wavelength, then we will get here the minimas. So in this way we have obtained the condition of path difference. As I have already told you, we will get a constructive interference when this path difference d sin theta is equals to m lambda, right? And if m is equals to 0, that will correspond to the 0 order, the central one. Here, no matter whatever is the wavelength, theta will be 0 in this case. So for other values, the maximas will occur at the different angles, and that will totally depend upon the wavelength of light used. As the wavelength increases, the theta will also increases, right? So the destructive interference condition here is when the path difference is equals to m plus 1 by 2 lambda, then we will get the dark fringes on the screen. Now in order to obtain the distance y, that is the distance from the 0 order to some spectral order, you can see in the figure the distance y. So in order to have this value y, you can see I can write down tangent of theta is equals to y upon d. Since the screen is at very large distance, means d is very large, so we can use tangent theta is equals to sin theta and nearly equals to theta. So that will be equal to y upon d. Now substituting this value sin theta is equals to y upon d in the condition of maxima, that is d sin theta is equal to m lambda. When I substitute y upon d on the place of sin theta in this equation, I will obtain the relationship y is equals to m lambda d upon small d. So this will give me the distance y where I have obtained a certain maxima or minima. As you can see on the screen, that in order to get this distance from this position to this position, that is why I have substituted the value of sin theta in this relation d sin theta is equals to m lambda. So I have obtained this relationship y is equals to m lambda capital D upon small d. So from here you can write down the value of y. This slide will show you the side view and the top view of the fringes that we obtain in the experiment. In the first figure, that is in the side view, you can see that the straight fringes on the screen, we get alternate dark and bright fringes. And in the top view, you can see that we are getting the central fringe as the bright fringe, since the path difference for this point will be equals to 0. The wave which is coming from source S1 and from source S2, they will be having no path difference when they will be reaching at the central point. So this central fringe will be the bright fringe, and we will get the alternate dark and bright fringes on both sides of this central point. So this was about the side view and the top view of the fringe. So this was all about the basics of interference and about the Young's double slit experiment. I hope you like this presentation, and in my next video I will explain you how to obtain the fringe width of these dark and bright fringes. Thank you.